Okay, we're gonna go on to chapter 3 today. We're gonna learn the Swiss Army knife of circuit analysis tools, nodal analysis, which is a really powerful technique for analyzing circuits. I don't want you to forget what you learned in assignment 2 in chapter 2, because nodal analysis is kind of like a jackhammer, and there's many instances where a simple screwdriver will do, and so assignment 2, chapter 2 is all the little screwdrivers and tweezers and things you can do to pick apart a circuit and understand what's happening in a circuit. If you don't get that, having a jackhammer at your disposal isn't really going to help you in all those circumstances, right? You need to know how the stuff really works, and that's what chapter 2 covers. Chapter 3 is just a more powerful way of dealing with things when they get complicated. Before we go too far into that, I had some questions about quiz 1, which closed last night, and you already got your score, which is awesome, so I don't have to grade it. And questions on so I mentioned I've been telling people that there is a review quiz for every quiz that you're going to take. And how do you find that review quiz? Well, what you do is when you go to the main course page, you click on the week that you're going. Now, I think a lot of people they just see, oh, I've got to do quiz 2 over here on my to-do list, so I'm going to click on quiz 2. I don't link the review quiz to that, so you have to know how to find it. Here's how you find the review quiz. There's a couple ways you can find it. If you click on the week that we are in, like what week are we in right now? We're in week 3. We're in week 3, Mark. And there's a quiz that's going to be due. In fact, you can see quiz 2 here is due February 11th. That's this coming Sunday, midnight. So that's because we have test 1 next week on Valentine's Day, February 14th. So you're going to take quiz 2, which is going to get you prepared for test 1 on Valentine's Day in class. And so yeah, if you just click on quiz 2, you're not going to find the review quiz, but you got to know it's there. So to find it, you go, oh, we're in week 3. Okay, so in week 3, this shows you everything that you're going to be doing in week 3. There's assignment 3, there's quiz 2, and there's quiz 2 review. You click on assignment 3, that has everything you want to need for the assignment. So you can find it real easily once you know where to look for it. Another way you can look for it is you just click on quizzes. If you click on quizzes, there are 2 types of quizzes. There are assignment quizzes, which are what you're going to get graded on. And then if you scroll down, there's practice quizzes, where you can do all your practice. And they're labeled accordingly. So that's how you find them in Canvas. So if you didn't get that, that's okay. There is a discard. There's one rule about quizzes, which is something like your lowest score will be discarded on the quizzes. Maybe even your lowest 2, I can't remember. But that's why I say that everyone should be getting 100% on all the quizzes, because all the questions are in the practice quizzes. You do the practice quizzes until you get 100. When you take the real quiz, you're going to get 100. It's really simple. That's how you learn it. Any other questions? Okay. Yeah, this week there's quiz 2. You can get a look at quiz 2 just to kind of see what it's going to cover. Pretty much the stuff that you did for homework this week. So you have an equivalent resistance. That's series and parallel. You got to learn how series and parallel works. A lot of people have issues with that. Here's where you're going to sort them all out. Another series and parallel. Another series and parallel. Another series and parallel. You're going to get this, and you're going to get it by constantly drilling yourself. Then you've got this. This is a voltage divider problem, right? You got a voltage across one resistor with 2 resistors in series. That's a voltage divider problem. These are the tweezers of circuits, and you have to learn these too, because it's going to make you better. Another voltage divider problem. Notice the sign polarity is different though on this one. That's going to mess you up if you're not careful. If you don't understand how signs work. There's another voltage divider problem with 3 resistors. Another voltage divider with 3 resistors, but the sign is different, right? So every permutation of these things you're going to get until you get it all figured out. What is this? What tool would you use on this one? No. It's a current divider circuit. Yeah, you're going to use the current divider formula on this one. Yeah. The current divider formula is faster. Yeah. Yep. So recognizing what tools to use, it doesn't tell you, but if you use the current divider formula, you're going to get the answer a lot faster, right? So remember, voltage divider formula, everybody forgets these right after. They just I'm never going to use a voltage divider formula. We're using voltage dividers all the time in this class. Current divider is really important. What's this circuit? Number 11. Current divider circuit, right? Another one. Another current divider circuit, but then sometimes the arrows are going the other way, so, and sometimes the source is in the middle, and the resistor's on the outside. Look at that. And then here's one with a dependent source. Well, this one's going to be interesting, kind of, working your way through that one. These two parts of the circuit are connected with one wire, but is there current flowing through this wire, do you think, on the base here? No. Why not? How can you prove that there's no current flowing on this wire? There's no way for it to come back, right? There's no way. Remember, KCL applies for regions of space and even beyond just one node, right? And if you circle this region and this region, you can't have current flowing from this part of the circuit to this part of the circuit without current flowing back on another pathway, right? You wouldn't have any current flow if you just have one wire, two parts. They're interesting circuits which are used to model things like operational amplifiers. They're exposing these to you now so that when you see them in chapter 5, it won't be so mysterious. But what you have to do is you have to figure out what's going on with these things. And, for this one, you got to figure out what IX is. Well, what's IX in this circuit? It's the current source, right? The current source going through this R. And this is a voltage source that's dependent on IX by some constant R. So if you know what IX, IX is IS, and they're giving you little r as 5 ohms. This voltage source, VC, how does that relate to VO? It's the same. And you can do KVL to prove that VO is the same as VC, just like KCL will tell you that IX is the same as IS, right? So you're applying these basic principles on circuits that are a little bit unfamiliar now, and you're going to have to kind of fall back on. This is all chapter 2 stuff, right? That's what test 1 is on. It's on chapter 1 and chapter 2. So you really want to get these things down because they're just so important. And remember, some of these questions are going to show up on test 1 in multiple choice form. You're going to have some multiple choice questions on each test, about 10 points worth, just to make it interesting. So you got to get those right because those are going to prepare you for taking the final exam. So you can't say, I didn't show you these questions in advance. You're seeing all these things in advance. Okay, all these things, and you can start working on these things right now. You've completed homework 2, so you can start the practice test. You can start, anytime you have some few moments, you can kind of play around with these things, get really good at it. This is how you're going to learn. So that's what's happening on quiz 2. That's the review. Take that as many times as you want. We are now looking at assignment 3, again, back to nodal analysis. And like I said, I don't want you to forget chapter 2 once you see chapter 3. So chapter 3 is introducing, again, these are methods of analysis for when the circuit gets really complicated. When you have a lot of circuit components, it's really hard to use the tweezers and the screwdrivers to actually solve it. Chapter 2, right? It's not, those aren't really that good for when things are complicated, but they really will help you in simpler circuits and when you're looking at like a small part of a larger circuit. All that stuff from chapter 2 is really valuable. But this is when you have a really big circuit and you want to make sense of it. And what we're talking about with nodal analysis is we talk about these things called node voltages, which are different from element voltages, and we're going to explain that in a moment. A node voltage is a voltage with respect to a reference node. An element voltage is the voltage across an element, the voltage across a resistor, across a voltage source. But if you know, and it really sort of depends on how you hook up your voltmeter. I'm going to draw a little sketch here of a circuit. I'm going to do multiple different colors so this all sort of, you can contrast it all, right? So here's a simple circuit. It's a simple voltage divider circuit, right? It's a 12-volt source. And you've got a 2-ohm resistor. You've got a 3-ohm resistor. And a 1-ohm resistor. And they're all in series. Now, the voltage divider formula, by inspection, you can kind of work it out. The voltage divider formula says that the voltage across the 1-ohm resistor is what? One-sixth of the total voltage, right? Because it's the 1 ohm divided by the sum of those resistors, which is 1 plus 2 plus 3, which is 6. So 1/6 times 12, which is 2 volts, right? And where should I put the plus sign on that voltage? I can say this is 2 volts, but which side is the high energy side? The left side, right? So I put the plus sign here, and the plus sign, and the minus sign, right? Okay, what about the 3 ohm resistor? What's the voltage drop across that? Yeah, it's 3/6, so it's 1/2 of 12, so it's going to be 6 volts, right? And the plus sign is on top, right? Everybody agree? And the bottom resistor, what's the voltage across that? 4. And which side does the plus sign go on? On the right. Current is losing energy as it drops through all those resistors, right? The current is going in a clockwise loop around there, positive current flow, losing energy across those elements. So those elements, each one of these blue numbers are element voltages. And how would we measure these element voltages in the lab? With a voltmeter. And where would you connect the voltmeter? In parallel with the element, right? So where would you hook the common wire of the voltmeter? So if I was going to measure the 6 volts on my voltmeter, and one of these things is common, and the other of these things is volts, right? Here's my voltmeter, here's the display. Which end would I hook up the common wire to? The minus side, the low energy side, right? And which end would I hook up the positive side to? The high end side, right? So this would kind of go here. And that would display 6 volts on the multimeter, right? On the voltmeter, it would say 6 volts if you have it hooked in the right setting. Looks like you have a question now. Go ahead. Why do we say -4? I didn't say -4. Notice how each voltage here has a plus and a minus on it. That's telling you how you're supposed to hook up the voltmeter so that you see the 4 volts. You could draw it like that if you want. Yeah, all kinds of little questions like this can throw people off track, so it's good to kind of surface those. Okay, so those are element voltages. Now there's another way of measuring voltage in the circuit, which you're going to learn this week, and then next week we're going to, are we going to do a lab on this? I think it's not going to be for a little bit longer. But suppose you have another voltmeter and you, let me see here, where should I put it? I'll put the voltmeter here. And again, we have this common and this volt. I know it's kind of hard to read, but I'm doing the best I can, right? Common and volts here. And what if we always put our common probe here at this node right here? And we're going to call this node VR. It's our reference node. And then we can move the volt side to like here, or we could move it to here, or we could move it to here. In other words, we're going to hold the common point fixed, and we're just going to poke around the circuit with the volt wire and see what the voltmeter says when we move it around the circuit there. We're going to call those node voltages. Those are, it's going to give us the voltage, the potential difference between any point on that circuit relative to our VR node. And so our VR node, which is our reference node, is sort of going to be assumed to be like 0 volts. It's the reference node. And we're going to see what the node voltages are as we explore that circuit with the red wire of the voltmeter, okay? So what would I see if I put the volt wire on this node here, right above the voltage source? What node voltage should I read there? Sorry? 12 volts, right? Yep, I should read 12 volts, which, because actually that is the voltage across the voltage source element in this case, right? Sometimes you will get element voltages, you know, when you're measuring node voltages. It happens. If the element is connected to ground, then the element voltage and the node voltage are going to be the same. We get 12 volts there. But what if we now move the wire over here? What is the voltmeter going to read when we move the volt wire to this node right here? Sorry? 10 volts. Why 10 volts? Because we lost 2 volts of energy going across that 1 ohm resistor, right? So the potential at that point is going to be 10 volts because it has to reflect that we lost 2 volts across that 1 ohm resistor, right? Now, what if we move it down to this point right here? What are we going to read on our voltmeter? 4 volts, because we lost another 6 volts of energy, right? So these node voltages are sort of like absolute height, you know, relative to whatever you're calling the ground of your circuit. Absolute energy relative to the ground of your circuit. Or if it's, you're talking about the, you know, the flow of water, it'd be like, you know, the height relative to the final, like, sea level of the flow of water. Sea level could be ground for the flow of water, you know, hydrology. Sea level is sort of like the low energy state. And you know, a water on the top of a waterfall, so many feet above sea level, you could kind of calculate the energy the same way, or intermediate steps along the way. So that's what node voltages are. They're relative to one particular point in the circuit. Now, if I move my reference node to like this point right here, just as a for instance, you could see how that would change all the values of the node voltages down here. Sort of depends on what you pick for your reference node for how they actually work out, right? If you decide to make sea level to be something like, you know, some lake, like Lake Tahoe, if you call that your sea level, then the real sea level is going to have like a negative voltage, a negative potential, because it's lower than Lake Tahoe, right? So your voltages, potentials will all sort of change. Okay, that's the concept of a node voltage. So that's really important concept, because you can do all the jackhammer stuff without really understanding what you're doing. But what you get from these numbers are these node voltages relative to a particular node in the circuit. So the way the nodal analysis works is you have to pick some reference node for the circuit, and then you assign node voltages. You assign node voltage like variables, right? You have to name these things to the remaining nodes. Then you apply Kirchhoff's current law to each non-reference node. In other words, you don't do KCL at the reference node, but you do it at all the other nodes. And you express the unknown currents in terms of the node voltages using Ohm's law. And I'll explain how that works in a second, but basically what we're writing is the sum of all of the currents, whether they're positive or negative, has to equal 0, flowing into or out of that node. And then step 3 is you solve for the variables of interest. Okay, and how does that step 2 work? How do you actually express unknown currents in terms of the node voltages? Well, for step 2, the current is the V higher minus the V lower divided by the resistance between. And this difference here is the element voltage. Another thing we can go back and look at, you'll sort of notice here that if you, in the previous slide, if you took the voltage to the left of the 1 ohm resistor and subtracted the voltage to the right of the 1 ohm resistor, what would you get? 2 volts. That happens to be the element voltage, the voltage drop across that resistor, right? So you can subtract the 2 node voltages to find the element voltages and the element of interest, right? You can always go back and forth between those. So that's the reasoning behind this. And if you want to sort of sketch out what a particular element might look like, here's a resistor. Here's V higher. Here's V lower. And the sign of the polarity is that, you know, V higher has a plus sign in front of it, right? So that has the plus side of the element voltage, and V lower has a minus sign in front of it. So that means there's a minus at that side, at that node. You're doing the element voltage, right? And so this element voltage is, you know, this difference here is V higher minus V lower. That's the voltage. And the direction of the current, again, using passive sign convention, is that you have the current flow this way, and here's your R. And so Ohm's law says, of course, that V equals R times I, where V is the element voltage, which is V higher minus V lower, which is the element. As the element voltage of a resistor. So this is sort of assuming that all the elements that we're doing these equations are resistors, but some of the elements might be current sources, and we can just use those currents because we're just summing all the currents. Now this doesn't make a whole lot of sense until you see it in action. So the next example, the next slide is going to show us an example of how this actually works. I'm going to have to move this below here because it's kind of hiding. That's not very convenient either. Well, there's an I2 up there that says I2. You can kind of see that on your handout. Here is a circuit. And it's convenient that the nodes have been labeled for us. So when you see a ground on a circuit, that's the reference node, right? So this is our VR node. And usually the reference node is the bottom wire of the circuit, but it doesn't have to be. But it usually is. And this is 0 volts. This symbol, by the way, is the symbol for ground. You're going to see a lot of that in the circuit lab class. The ground, that's the reference node. When you see that on a circuit, that means that is sort of assigned 0 volts. Grounding is another, it's a sort of a safety mechanism too. A lot of our electrical devices are grounded. And literally when, you know, if you're an electrician, when you plug in something to like a socket, you know, a 3-pronged socket, which one of these is that? The little circular one, right? The two prongs are not ground, right? So the ground, actually, you know, a typical power socket looks like this. This is the ground. And literally, if your house is wired correctly, that ground will actually come out of your house and go to like a metal pipe, or maybe your water mains or something, something that's actually going into the ground, and it'll be attached there with a big cable. and that keeps the reference voltage of your house at a known thing. So you can't build up. Sometimes if you don't have that grounded, you can get potential buildup, and then you can get shocks and stuff. It can be dangerous. So that's a really important part of the wiring of your house, to have a ground of your circuit. And that's the same effective thing on our circuits that we're working in the lab. Now, when you look at a circuit like this, you can label now these things. You can see that we've labeled V1 and V2. This is a variable. It's a node voltage. It's a variable voltage that we don't. It's an unknown voltage that we haven't determined what it is yet. And we're going to use nodal analysis to solve for V1 and V2. And once we find V1 and V2, then we know the element voltages for all the circuits. And you can imagine that there is an I2 flowing across the R2 resistor, and an I1 flowing down the R1 resistor, and I3 flowing down the R3 resistor. And the direction of these guys is implying the polarity of the sign labels, right? If I1 is flowing down through R1, then the plus sign should be on top. If I3 is flowing down through R3, the plus sign should be on top. And if I2 is flowing through R2, the plus sign should be on the left, because it's flowing into the plus sign. That's all passive sign convention. You're going to do that for all of your resistors like that. Label the polarity that way. Now, the I1 from this current source is also flowing into the V1 node from the left. The I2 current source is leaving the V1 node, and it's entering the V2 node, isn't it? And so we can write KCL. This is what the nodal analysis method means, is you're going to do KCL, and you can do KCL at node 1. And by doing KCL at node 1, you're just going to sum all the currents entering or leaving the node, right? So you're going to have plus I1, the current entering the node, right? Oops, this should say I2, sorry. Nobody called me on that. How come nobody said anything? You were going to, but you just wanted me to look stupid. Yeah, no, if I make a stupid mistake like that, you guys should tell me, because someone else might be kind of confused, and they might just be really hung up on something during the lecture. Yeah, should it be I1 plus I2? Well, remember when we do KCL, KCL says the sum of the currents like entering the node has to equal 0. And is I2 entering the V1 node? No, it should just be I2, because there's a current source I2 up here. That current source is controlling the current from, through this whole branch here. It has to be I2 throughout. Yeah. Okay, but again, summing all the currents flowing into this V1 node, right, we're going to say plus I1. What's another current flowing into the V1 node? Sorry? Well, yeah, but because all the other currents are flowing out of the V1 node, right? But you can just put minus signs in front of those things and say, well, you got the minus of that current flowing into the node, right? So give me another current flowing into node V1. Minus capital I2, right? Because capital I2 is flowing out of the node, right? What else? Minus little I1, right? You see little I1. Minus little I2, right? And those have to add up to 0. So you can go through those steps, but actually, once you get the hang of doing nodal analysis, you can skip labeling the little I1s and the little I2s. because you can do those by inspection. It's really easy using nodal analysis, right? So the way we do it, and once you get good at it, you'll see how easy it is. It's going to be I1 minus I2. Those are given to us. They have to be given to us as some value. And then minus, and then we think of what is the element voltage for R1? What is the voltage across the R1 resistor? Pardon me? I1, R1, yeah, but suppose we're not going to use the little I1s anymore, the little I2s. So we have to do everything in terms of the node voltages, right? That's what nodal analysis means. You're going to express everything in terms of V1 and V2. So given V1 and V2, what would be the node voltage across the R1 resistor? Well, that's not a voltage, that's a current. What's the node voltage across the R1 resistor? V1, just V1, right? Because it's the difference between two node voltages, right? It's the difference between V1 and what? The reference node, which is what? 0. So in other words, I can take and say, well, we got V1 minus 0, because that's VR. That's the reference node, right? This is VR, which equals 0 volts, right? That's a V, that's an R. So it's like V1 minus 0 over R1, right? And then what's the element voltage across the R2 resistor? Again, express it in terms of V1 and V2. V2 minus V1. Well, but that's going to be, yeah. If we want to define I2, we want to replace what we wrote with I2, right? We're going to say, using the same polarity, right? Say it could be V1 minus V2, right? Because the V1 is associated with the side of R2 that we've labeled the plus sign that we've had to label because of passive sign convention for the I2 current, right? And the V2 has a minus sign associated with it. So we say minus V1 minus V2 over R2 equals 0. Because this is the definition of I1, and this is the definition of I2. Okay, that's one equation. Now, the same thing for node 2 is going to be done, and I didn't leave a whole lot of room for that, so hopefully you have more room than I do. So in node 2, we look at all the currents entering node 2. What are we going to say here? Just in terms of the currents now, forget about the voltages we've got. What do we got here? We can box this if you want. This is your first node equation. And you've got capital I2 entering, right? And then what's leaving? Or what's another current that's entering? Plus little I2. And you got I3 leaving, so you got to put a minus in front of that, right? And so the equation is going to be written as I2 plus, and then we've got V1 minus V2 over R2. Okay, again, that's our I2. Then we got minus, and then our I3, which is going to be V2 minus 0 over R3 equals 0. And that's our second equation. So we now have two equations and two unknowns. We can solve for V1 and V2 using free mat, or if you want to do it on paper, you can. And then once you have that, you can figure out everything else in that circuit. Once you know what V1 and V2 are, you can find all of the element voltages across those resistors by subtracting the node voltages, and then you can find the currents by taking the element voltages divided by the resistors, right? So from that framework, it's pretty cool, right? Once you know those node voltages, you can figure everything else out. so you basically solve the whole circuit just by doing those two equations. It's a really systematic way, and if you have more nodes in the circuit, you can easily expand this. You can have a 4x4 matrix to just plug that into FreeMat. You could have a 10x10 if the circuit gets really complicated. You can basically solve any circuit using nodal analysis. It's a really powerful technique. Okay, and so the other way we're going to do this, and this is a slight. So this way is actually correct, but it's sort of a little complicated in that we're sort of labeling these little I1 currents, and then we're defining it in terms of that. There is a slightly better way, and the way we actually, and this is sort of the way the textbook actually does it, is the way we actually can think about it is in terms of this. We're going to say sort of a more systematic way. And the more systematic method is to assume that well, let's see. We're going to assume that all of the unknown currents are flowing into each node, and we'll flip those things around as we go, as we address each node. And what I mean by that is, what if we assumed that we want to find this current and this current, instead of the way we did it here, where those currents were flowing in the opposite direction? It's a small change, right? We're just changing the sort of the understanding of how the currents are flowing into or out of those nodes, so that we're going to define those currents at each node as if all the currents through the resistors are flowing into the node, and we're just going to define the element voltages with that reference direction and add them up really fast. And this becomes very mechanical and systematic when you do it this way. Let me explain how that works. So what we do is, if we express it this way, and just sort of, now we're just sort of looking at this point right here, if we label I2 going this way, how do we put the plus signs across R2 using passive sign convention? How do we put the plus and minus signs? The plus sign for R2 should be on the left or the right? On the right now, right? And the minus sign should be on the left, right? Because passive sign, you gotta follow that, right? And where should the plus sign for R1 be? At the bottom, and the minus sign would be somewhere like here, right? If we want to think of I1 flowing that way and I2 flowing that way, then we can write these equations really systematically. And when we do it for node 2, we're going to flip it so that they go the other way, and we'll erase it and do it the other way. So let's see how that works. So node 1 then becomes I1 and I2. We can't really mess with those. Those are fixed. So we're going to have I1 minus I2, right? And then we're going to write plus, and the element voltage now is going to be the +1 minus the minus. Well, the +1 is 0, right? So plus 0 minus, and this is V1 and this is V2, right? So 0 minus V1 over R1. That's the current I1 now flowing up, right? You see that? It's the opposite of the current in this one, which was flowing down. The current in this one was V1 minus 0 over R1, right? That's I1. If we change the direction of I1 so it's now flowing up, we got to change the polarity of that thing, so it's going to be 0 minus V1. And that means we can just put a plus sign in front of all these currents, which again makes it really systematic. That's not a plus or minus. I just wanted to highlight that. And then the plus sign, and then we write the current for I2. And how would we express the current for I2 now that it's flowing to the left? With those polarities that we've labeled passive sign convention, how are we going to express I2? V1 minus V2 over R2, right? Not quite. Which side of the resistor has the positive sign now? V2 has the positive sign, right? So it's plus V2 minus V1 over R2, right? And that equals 0. See that? That's a little bit easier because in this case, you had to kind of look at those current directions and then put the minus sign here, right? And you know, it's doable either way, but this one is a little more mindless. It's mechanical. You just do it the same way every time, and then you don't have to think about it. You don't think about the direction because it's always going to be flowing into the nodes. David. When we're considering R1 at the plus sign, yeah, that's what I drew right here. Did you see that? Did you miss that? Yeah, we are assuming, and why can't I get my color changed? Not able to change color. Well, I guess we're in blue then for the rest of the lecture. Yeah, that's why I labeled this plus sign here and this minus sign here, because if the current is flowing up, then the high energy side is going to be on the bottom, right? It's purely arbitrary, right? We're just doing this to define these equations properly so that they're all consistent. Yes? You're going to get a negative current, but you're still going to get a positive voltage. Possibly, yeah. I mean, these are all variables, and whatever we crank out is the answer. You know, yeah. You're saying something. You're saying if you want to know the voltage across R2, you're still going to get a positive voltage, but you're going to get a negative current. Well, not necessarily. What I want, so I don't know what V1 and V2 are, but let's put some numbers on there, then maybe it'll actually make a little more sense, right? Suppose, and hypothetically, right, maybe V1 is 3 volts, I don't know, and suppose maybe V2 is 9 volts, right? Okay, let's put some numbers on there, right? We're not going to know those until we do the analysis, right? And once we've solved the system equations, then we'll get a V1 and a V2 value. But suppose we end up doing all that and we got these numbers that V1 was 3 volts and V2 was 9 volts, right? So that means which way is I2 really flowing? To the left, right? Yeah. So I2 is going to be positive. Yeah. Yeah. Now, it's just as likely when you're doing these things that this could be 9 volts and this could be 3 volts. I don't know, right? And in which case, which way is I2 really flowing? To the right, right? It all works out. It's a consistent set of equations. As long as you follow these steps rigorously, it'll all work out just fine. Do I label the drop across R2 as positive or negative? I don't care. I label the drop across R2 if I'm talking about I2 flowing to the left as I label it as V2 minus V1. Whatever V2 and V1 are is going to affect the actual sign of that voltage drop. You know what I'm saying? You won't know that until you actually grind through and get the answers for V2 and V1. It's all just it's a labeling, consistent labeling, and processing technique. I think. Why is it 0 minus V1? Because I'm assuming in this case that I1 is flowing up, and passive sign convention means I've got to put the plus sign at this end of the resistor and the minus sign at this end of the resistor. And you missed this part, but I've decided to call this, which is called ground, the reference node, which is 0 volts. So it's 0 volts minus that. Yep. Uh-huh.
Why is it sometimes
Why is current represented as an element and sometimes it's represented outside? Well, you might be referring to like sometimes you see current like that. Is that what you're saying? Sometimes you see it like that. Or what? Oh, yeah, these are different things. This is like a 5 amp source. This is a 10 amp source. These are actually fixed sources. These are current sources. These are not current labels. These are current sources. Well, they're capital versus lowercase. Yeah. Yeah. Yeah, it's amazing how many ways you can kind of mess things up, right? And for node 2, then we switch again, and I wish I could change colors, but I've somehow, oh, there it is. Oh, wait, it came up. There it goes. So for node 2, let's do it this way. Let's assume that I2 is going into node 2 and I3 is going into node 2 as well. Oops, that should be an I in front of that. It would help if you had different colored pens in this class. If we're going to talk about I2 flowing into the V2 node, then we have to put the plus sign to the left of R2 and the minus sign to the right, right? If we're talking about I3 flowing up, we got to put the plus sign on the bottom and the minus sign on top. So when we do the node 2 equation, we're going to say, well, we got to add all these things. We got I2 flowing into node 2, right? So I2, capital I2 is going in, right? Plus little I2, which is what? How do we define little I2 now that we've decided that it's going to be flowing to the right? Yeah, the V1 now has the plus sign associated with it, right? The red plus sign here is closest to the V1 node. So it's plus V1 minus V2 over R2. And if I3 is flowing up from through the R3 resistor, what's the last term of that equation going to be, Isaac? Okay. David. What's the node voltage here? That's a V2. Yep, equals 0. Mm-hmm. Now that's the same equation as we have here, and maybe you don't agree with me, but this is actually a more mechanistic way of doing it. Just always going to write those equations, assuming the currents are flowing into the nodes. And the element voltages are always going to be the far node voltage minus the node that you're flowing into. Notice this term here is always the node that correlates with node 2, right? So the second one is always going to be the node that you're looking at. The first one is always going to be the far node, right? It's the far node minus the node that you're flowing into divided by the resistor. Very mechanical, right? You just do that over and over again, and it works out just fine. So that's what this shortcut is saying. The direction of the assumed current does not matter. Always assume all unknown currents are into the node, and so therefore any resistor value is going to be the V far minus the V near, or the V node that we're actually doing over the resistor. And that's basically it. Once you know this, it's really easy to do. We ran out of time, but we're going to have a real circuit now with actual numbers on it, and we're going to crank through this on Wednesday. Sorry about the gap of the lab, but I had to sort of squeeze that in. So we'll pick this up on Wednesday, and you'll actually see how straightforward that is. Isaac. No, we have a test next week, Tuesday. No, not Tuesday. Tuesday's lab. It's next week, Wednesday. It's the 14th. What day is the 14th? It's Wednesday. Next week, Wednesday the 14th. It's a 1-hour test. Yeah. I'll give you a practice test later in the week. We'll give you a practice test later in the week you can look at. And then we can go over the practice test on Monday. And any homework questions you still have or quiz questions you have from the quiz, all that's going to be reviewed on Monday. Then you have the Tuesday lab. You can pull me aside if you have any questions still on the practice test. You can pull me aside during the lab. And then you take the test on Wednesday. You've got plenty of time to make all this clear. This will not be on the test, so you don't have to worry about this stuff that much. But it is due on Sunday. And actually, by doing this, you're gonna get further practice in writing KCL and KVL, and all this stuff will start to make sense. So doing this homework assignment is going to help you on the test anyway.